Yo, what's up everyone? Patrick here, welcome back. And in this video, what we gotta do is we gotta find the symmetry of this function here. Notice it's a pretty complex function. We got cos squared x minus 3 times sine squared x plus 3 times x squared minus the absolute value of x. So when they're asking for the symmetry, we gotta find out is the function odd, even, or neither. Another word that you might see come up is parity in certain textbooks, or certain teachers or profs might use the word parity, find the parity of a function. Same thing as asking for the symmetry of the function. Now, before we get into this function, I actually want to talk about cos x and sin x separately and their symmetry a little bit, because notice we're going to be dealing with both of them here. So first off, cos x, how does this function look like, just graphically? Well, we know it starts at the max when x is 0 and just continues to go like that. And then same thing to this side. So if you look at it visually, notice that cos x, it's an even function. This is an even function because it's symmetrical about the y-axis. Right? If we take this portion and reflect it, we would end up with this portion. Now, in general, when a function is even, what does that mean? It means f of negative x equals f of x. When a function is even, this holds. So if we apply this to cos x, what that means is cos of negative x equals cos x. This is a fundamental trig identity here. And it's basically derived because of the symmetry of cos and because of this property for an even function. So this identity we're going to be using in the process of finding the symmetry of this function. So I want to go over this stuff beforehand, these fundamentals beforehand. So we know cos of negative x equals cos x because cos x is an even function. Now what about sin x? Well, sin x, the way the graph looks like that, right? This keeps going, this keeps going. So sin x is an odd function. And it's a little tougher to see visually, but basically if you were to take this and rotate it about the origin, you'd end up with this portion of the graph. Or another way to think about it is if you took this portion here, right, all of the portion of the graph for all the positive xi's, if you reflected them in the y-axis and the x-axis, you would end up with this portion here. Again, it's kind of tougher to see, but if you took this, draw it out on the side, took this, reflected it in the y-axis, then reflected it in the x-axis, you'd end up with this portion here, right? So sin x has point symmetry, or it's rotationally symmetrical about the origin. So what that means for an odd function in general, f of negative x equals negative f of x. Right? So if we take this property for an odd function and apply it to sin x, what that means is sine of negative x equals negative sine x. Right? That's another fundamental trig identity. And it's because sine is an odd function. Right, so I'm going to take that identity and I'm going to write it up here. And we're going to be using both of these identities for this process. So when we're looking for the symmetry of a function, what do we got to see? We got to see whether f of negative x equals f of x, then the function is going to be even. Or if f of negative x equals negative f of x, then we know the function is going to be odd. And then if neither of these hold, then the function is neither even or odd. So f of x we already have. This is the function here. Now let's start off with negative f of x. Let's get this portion here. I feel like that's the easiest. Negative f of x is just simply, we could put a negative in front of everything. Right, so that's what negative f of x is going to be. Another way is you can actually take this negative and distribute it maybe in this bracket. So this would change to 3 minus cos squared x. Or you could take this negative, distribute it to this bracket. You got to pick a bracket for it to distribute to. Can't distribute it to all of them because all these brackets are multiplying. But for now, I'm going to just keep the negative on the outside. I feel like that's going to be easier to compare when we find an expression for f of negative x. Right, so we got the function f of x, we got negative f of x. Now what we got to find is f of negative x. Right, and then we got to see, is this expression that we're going to get, is it going to equal negative f of x, or is it going to equal f of x, or neither? So what we would do for this, so let me actually kind of just circle these off so you're not getting confused. Right, these aren't like steps here, these are separate things, separate expressions. So f of negative x, what we're going to do is we're going to be using this, and we're going to plug in negative x for all of the x values. Now, if you remember, cos squared x, another way to write that is just cos x squared. Sine squared x, same thing. Or basically sine any exponent. Let's call it an exponent n, right? That's going to be sine x to the power of n. Same thing, cos. This could have been an n here to generalize it a little further. Right, so when I'm plugging in this negative x here, I'm going to keep it in this format. So this bracket would be cos of negative x minus 3, sorry, this cos squared x, it's going to look like that. And then this sine squared x, if I plug in negative x for the x value, that's going to be sine of negative x. That's going to be squared. That's going to be plus 3. And then this remaining bracket, I'll write it over here. We'll have negative x squared minus the absolute value of negative x. Like that. Right, so just took this function and plugged in negative x for all of the x values. Right, so now let's try to simplify this a little bit and make it comparable to these. So, give myself some room here, f of negative x. Now, cos of negative x, we discussed that that's just equal to cos x. So, I'm going to rewrite this cos of negative x as just cos x. And that's going to be squared, that's going to be minus 3. Sine of negative x is negative sine of x. So I'm going to rewrite this bracket as negative sine of x. That's going to be squared, that's going to be plus 3. Negative x squared, if we show the work over here, there's like a negative 1 here. So it's like the negative 1 goes to the power 2, and then the x goes to the power 2. Negative 1 to the power 2 is just positive 1. X squared is just x squared. So this here changes into x squared, and the work for that is shown over here. Because if you remember exponent rules, if you got something like this, right, things are multiplying, everything goes to that exponent if these expressions are multiplying. And then we're going to have minus, now the absolute value of negative x. What's that going to be? Well, we know the absolute value just changes everything to a positive. So it's actually just going to equal that. In fact, the absolute value function, it's an even function. Right? If we draw it symmetrical about the y-axis, so we know f of negative x equals f of x, which means that this is going to hold. But if you want to kind of show it maybe a little bit more algebraically, very similar to that exponent rule I just went over, if you got two expressions that are multiplying in an absolute value, basically you could take the absolute value of both of those expressions separately and then multiply them. So there's like a negative 1 in front here. So applying this, it's like the absolute value of negative 1 times the absolute value of x. What's the absolute value of negative 1? It's just positive 1. Absolute value of x is just absolute value of x. All right, so different ways to explain that this is equal to that. And so what we would end up with over here is minus the absolute value of x, like that. And so let's continue to simplify this, put it in a nicer format. So cos x squared, I'm going to put it back into that format. That's just cos squared x minus 3. Now what's negative sine x squared? Well, that exponent rule again applies here, because notice we got a negative 1 that's multiplying by the sine x. So negative sine x to the power 2, it's like negative 1 to the power 2, and then sine x to the power 2. Negative 1 to the power 2 is just positive 1. That's going to be sine x to the power 2, which is just sine squared x. Right? Any even exponent here, you're going to end up with sine to that even exponent, because that negative 1 is going to change to a positive. Negative 1 to any even exponent is going to be a positive 1. Now, if this was an odd exponent, let's say this was like 3, then we'd have negative 1 to the power of 3 sine x to the power of 3. Then that negative would still have to stay, because negative 1 to the power of an odd exponent stays negative. Then we'd have sine 3x, like that. Right, so just be careful with that, odd versus even exponents. But in this case, we're dealing with an even exponent, so this just turns into sine squared x plus 3 x squared minus absolute value x. And so this here is the simplified expression for f of negative x. And f of negative x, does it equal negative f of x or f of x? Well, notice it equals f of x, the original function. This bracket is the same, this bracket is the same, that bracket's the same. Right, so because f of negative x equals f of x, it means f of x is an even function. So what made this kind of tricky is knowing these trig identities here, these fundamental trig identities, and then maybe dealing with this absolute value right there.